let's get started with the very last talk of this conference. And the speaker is Alejandra, and she will tell us about near ADS2 spectroscopy. Please start.
Okay, thank you so much. Unfortunately, I don't know who's introducing me, but thank you so much for the introduction. Well, there's a few things. So I'm the last. I think the first thing that I wanted to do.
Masahito Yamazaki.
Oh, Masahito. Oh, hi.
Hi.
I can't see you, but
okay, maybe I was in the place where you cannot see me. I'm jumping here.
Oh, okay. Hey. Okay, very good. So the first thing I wanted to do was I think we should all give a round of applause to the organizers for having this conference, for having it in this hybrid setup. So clap to all of them. Thank you so much. I'm very, I've been able to join some of the talks, and I've enjoyed it quite a lot. And and it's really a pity. I feel very sad that I couldn't join you, but I'm very happy that they could accommodate for this hybrid setup. So as the last one, I'm also going to, I'll do my best to make sure that I don't go over time and that you guys can go have lunch and go back home. I know there's some anxiety at the very end of a conference to have it over with. So I'll try to do my best. So, okay, very good. So with that said, let's dive into the subject for today, near ADS2 spectroscopy. I hope you can hear me okay. If not, yes, okay, I see some nodding. I think it's fine. So let's dive in. So the program basically that we're looking for, so the motivation in a nutshell, is black holes. We basically want to understand the statistical description of black holes. We want to be able to design and control the systems with the aim of interpreting the entropy of the black hole as basically counting numbers of microstates. Okay, so I don't have to say much more in this type of audience, but like the type of questions, like what was motivating this work and what I'm going to discuss today is that in a holographic setup where we're supposed to have the tools to build this statistical description, there's a few questions that are important to emphasize. So for example, so a lot of times we focused on this part on the area law, and this basically hints to a very universal description of black hole entropy, but I really wanted to be more precise about which aspects of this description are really universal, and basically which aspects of this description, so as I go from here to here, which aspects of this description actually depend on the background that I have on the black hole, and which aspects depends on the surrounding, so where the black hole is embedded in. And more precisely, what I mean by this, so if I refer to background, colloquially speaking, during this presentation, I mean basically the parameters of the black hole, properties of the black hole, properties that might not come immediately into the area law, but they might be important in order to understand what is the statistical description. And by surrounding, I basically mean what is the theory? Okay, so where is this black hole contained? And in the most basic setup, it will be a context of, for instance, having black holes that are asymptotically flat versus black holes that are asymptotically ADS. So this can be something you can think of like the surrounding. Okay, so not just properties of the horizon, but actually the environment that holds the black hole and how that affects this interpretation. So with that said, so this is basically the overall picture that we have in mind. The way that we're going to try to understand the answers to these questions is basically using, last thing. So from this point of view, so having all what I hope to convey as I describe aspects of backgrounds and surroundings, in some sense, what I'm aiming for here in building the statistical models, I'm trying to understand, do we really need a periodic table for black holes? Okay, so can you think a little bit in terms of black hole chemistry, that there might be different types of microstates, different types of atoms and protons and electrons, and kind of like how do you put them together and how do they affect basically this description. I'm getting to this part here, okay? So this is the question. Okay, so sorry. So the strategy that I have is the following. So it's a very simple, it's very natural for a community of string theorists. This is not going to be shocking to anyone, but what I'm going to do is basically ask myself the question of setups where we have control in string theory. So we usually have control when black holes here are at extremality. And the big thing that I'm going to emphasize here is that I'm not going to look at some random, basically your favorite low energy theory. I do want to think about how I will build this statistical description in a context where I believe I have a unique description of this black hole. So I'm going to be putting this black holes inside of supergravity, which will be very important. And as I start from the extremal background of these black holes, what we're going to do is that we're going to kick them. And by kicking them, basically, I mean, well, sometimes I literally mean kicking them, but no, I'll mean more seriously. I just mean that I'll be turning on the temperature, okay? So we will start from an extremal description where we have control, well, where we have a lot of symmetries, and then which allows us to say something very precise, and then we're basically going to turn on this temperature. And a lot of this procedure, so a lot of what happens here is very universal. A lot of the things that happen here are also universal. But what I want to make emphasis today, I don't want to focus too much on things that are universal, that are shared. I want to focus on non-universal aspects of this construction, okay? So things that are not generic and that will depend basically on this background, on this black hole. And the two things that I'm going to focus on today are basically what are the spectrum of operators that appear as you do this analysis, and what are the interactions that these operators have, okay, with the relevant sectors. So this is the basic strategy of the talk and how it's going to be organized. Now, this I don't do alone. I have an amazing collaborator with me in this journey. So we recently, last week, we put out a paper with Evita. Evita's a PhD student here at the University of Amsterdam, and I should advertise, she's applying for postdocs this year, so pay attention. And she's an excellent candidate for your positions, so I'll keep on emphasizing that, okay? So all the details also, I'm going to not go into a lot of the equations and stuff, but you can, if you're interested in more details, please go to this reference. There's also another series of papers that I've been working on, which also include Evita, Chiara Toldo, who's a postdoc in Amsterdam, Juan Pedraza, who's currently now in Barcelona, my prior PhD student, Victor, and a student of Wei Song, Boyang Yu. And it's something that incorporates, these are analyses that incorporate rotation. They fall in a very similar spirit and motivation as the one that we're doing right now. So if you ask me at the end of the talk, what happens if you add rotation, I'll let you know. But today, what I'm going to tell you about, I will not be incorporating rotation. We're going to just look at static configurations. Okay, so let's get started. Okay, so let's first, I will tell you a little bit about some universal aspects just to set up the stage, okay, so that we can understand, roughly speaking, what are we doing. So the setup is the following. So I'm going to be looking at black holes in 4 dimensions. These are going to be solutions of n equal 2 supergravity, the U1 to the 4th supergravity. We're going to be discussing both the gauge theory and the ungauge theory. So in this case, the space-time is asymptotically ADS4, and the ungauge theory, the space-time is going to be asymptotically Minkowski 4. And this basically, this theory, if you want, if you're familiar with supergravity, when G is equal to 0, this is going to be basically the STU model, a model that I grew up with back in the day. And in the case of the ungauge theory, this U1 to the 4th is basically a truncation of n equal 8 SO8 supergravity, okay? So that's the supergravity, the consistent truncation that we will be studying, and we'll be looking at solutions there. Now, this theory contains a bunch of stuff. So it basically contains 4 gauge fields. So that's basically the information that I'm listing there. And we'll be looking at ionic solutions. That means we're going to be looking at solutions that carry both electric and magnetic charges. There's as well matter in this theory. So the thing that you need to know is that there's 3 scalars that I'll be calling phi I, and there's 3 axions that are chi sub I. Okay, so this is what we usually refer to as the moduli, and they're basically scalar fields in your supergravity description. Now, our starting point, so we're going to be looking at solutions starting from their extremal limit. So basically when the temperature is equal to 0. And extremal black holes have this fantastic property that they have a near horizon region. So you can go into, there's a long throat that describes the geometry. And for these backgrounds that basically only carry magnetic or electric charges, the near horizon geometry is described by ADS2 times S2. And one thing that I would like to remind you is that these solutions are also basically very well characterized by the attractor mechanism, where basically these scalars become constant on this geometry. Okay, very good. So that's the initial setup. Now, what we're going to do is that we're going to heat up the black hole. Okay, so ADS2 is a little bit fragile. It's a little bit problematic from that point of view. It doesn't like to be added energy. And so as we try to see how the black hole responds, because as physicists, that's how we understand systems, right? We sort of tamper with them and we see how they respond. This is what we're going to do today. And this will fall into the subject of near ADS2. So if the geometry here, so I'm depicting basically what am I doing in terms of this background. So if in the deep part of the near horizon, you have an ADS2 geometry that represents the extremal black hole, I'll be turning on the temperature, and this basically makes me move away from this ADS2 region. And that's why I'm depicting by this deformation here. Why? So I'm changing the size basically of the sphere, which will basically increase the entropy of the solution. And then eventually, if you follow this through, you would get to a solution that basically has a non-trivial radial profile. Okay. Now, why is this an exciting setup and a useful setup? Well, it was basically mentioned. So let me focus on this near ADS2 part that is down here. So it was noticed in these references that this part of the geometry has a very beautiful, elegant, and universal behavior, which is basically given by what we call nowadays JT gravity, okay, Jacobi time-to-point gravity in 2 dimensions. So the gravitational back reaction is basically dominated. So you can build an effective theory around this region. And the dynamics, the gravitational dynamics, is basically described by a very simple action of that form, and Y obeys this constraint equation. But in terms of operators, basically, you're saying that you're turning on, so as you're looking into the near ADS2 region, the folklore is that you're basically turning on an operator, an irrelevant operator of conformal dimension 2, and thus driving the system away from extremality, turning on some temperature. Okay. Now, the nice thing about these statements is that there's a lot of universality in this deformation. So it's important deformation to consider. Basically, the goal, as you break the symmetry, so turning on this operator will break the symmetries of ADS2. So that's why I write down here, it's near ADS2. It's not quite ADS2. And the Goldstone modes are basically described by the Schwarzschild effective action. So this is basically this field Y coupling, basically making physical large diffeomorphisms that live on this ADS2 region. And this physics of the Schwarzschild effective action basically accounts for the entropy of the black hole. It captures the first correction in temperature. And also the reason why this model is very exciting is that a lot of aspects that are contained in this theory are very well described by an SYK model, okay? So it's not quite the dual, but there's many aspects that SYK shares with this JT gravity theory. Very good. So this is roughly what is happening to us, okay? So this is the story so far. Now, in the context of black holes, so there's been a lot of emphasis on this 2D theory. I should mention that even early in the day, these were some of the initial work on the subject. This was connected to the Rice-Nostrum black hole. So a lot of, and this picture basically, and the justification of using this theory was made for charged or both electric and magnetic charged black holes. But a lot of the literature just referred to the Einstein-Maxwell theory. So they didn't have anything else, just metric and the gauge field, which is perfectly fine choice. But one of the things that we're going to do is that we're going to actually not just look at the Einstein-Maxwell theory, we're actually going to look at the supergravity theory. Okay, very good. Now, so that was universal things that happen to black holes. Maybe I should pause because I can't, you're very tiny. So if there's any questions so far, or am I going too fast?
Any question? Okay, yeah, I think it's fine.
It's fine? Okay, very good. So we're all experts in JT gravity. That's great. Okay, good. So now let's explore some aspects of this that are not universal. Okay, so what are things that if you actually put this black hole in a UV complete theory, what should you expect? Okay, so let's move away from toy models in some sense. Okay, so when I was describing this sector and I was describing the dynamics that happen here, I wrote like ... And I basically want to tell you that what's happening in that ... okay? And I want to make a big fuss that it's super interesting what happens in that ... okay? That's what's going to happen to you. So, so in that context, there's going to be those ... dots in this talk are going to be filled in by actually putting these things inside of supergravity. I am going to make a difference between the gauge case and the ungauged case, and something that you'll have to keep track of. So remember that these theories have 3 scalars and 3 axions inside of them, and these guys are going to play an important role. So all of these features are going to play a very important role, okay? So the first thing that we're going to do is that we're going to look at the spectrum, okay? So we're going to basically say, okay, so when you back react the geometry, so when you move away from this ADS2, so you start here and then you kick the guy up. So of course, yes, there's going to be a deformation of the size of the sphere, that's fine. But we want to do a good job here, so we don't want to be sloppy. And so we also have to, in principle, if you want to do this properly, you have to see if the metric is back reacting and if the scalar fields are back reacting as well. I should just say, I'm not writing down the field strengths because you can actually integrate them out in this context, just because of the very nicely symmetric configuration that I have here. So that's why I'm not writing down a back reaction for the field strength. They're basically just govern whatever you do here, and here is going to dictate what the field strengths are doing, okay? But this is the first step, okay? So let's do a good job at back reacting the geometry. And basically what we want to do is that we want to make sure that there will be mixing between these different components because these geometries are messy. And so we want to make sure that we basically decouple appropriately the matters degrees of freedom. And so one of the first things that we're going to do is that I'm going to report on what are the conformal dimensions. So basically, what are the operators that you appear? So how do you interpret these guys as operators in this context? And what are their conformal dimensions? Okay, so this is the formula in the case of ADS2 of how the conformal dimension is related to the mass of the field. Okay, so that's it. This is not super difficult, but one has to do it. Okay, now, even if I just talked about this, and I stopped here, and then I told you what is the spectrum, I want to give you a spoiler right now, just so you keep on paying attention and you don't decouple too much. There's going to be already surprises here, things that you perhaps, well, at least I was not expecting. I thought that this part of the story was going to be quite boring and straightforward, and I was surprised. So I hope you will be too. I don't know, you'll tell me or not tell me. Okay, very good. Now, the other thing that we're going to do, in addition to reporting to the spectrum, as I told you at the beginning, we're also going to report on the interactions that you find. So basically, we're going to see how these fields all communicate with each other. And so in that context, we're going to basically build an effective action that will have a part of the theory. So this is starting from the ADS2 background. We'll basically have a free part that describes, so here, so this is going to be basically the operator content. I change a little bit the notation relative to this one, because I do want to stress that one has to properly build the orthogonal degrees of freedom that decouple, at least in the free limit. And so that's why these guys are basically, they're going to be some complicated linear combinations of those other two. Okay. And the interactions that I'm going to discuss today are basically interactions that involve 1 power of y of this field that appears in JT gravity, basically coupled to 2 times the operators that appear here. So these are cubic couplings in this context. And they appear in all sorts of arrays. So you can have the simplest one that you just have y times 2 zetas, but of course, because this theory has derivatives as well, like there can be as well derivative interactions depending, like the kinetic terms in supergravity, they're not always minimal. Okay, but in any case, the end point is that there's an effective cubic coupling in this construction. Very good. Now, what am I going to do with those interactions? So what we will report on is basically how these interactions affect the 2-point functions of these operators. So if you don't have the interactions, there's a free part for the 2-point function, which I didn't write, but it's basically what you get if you just compute correlation functions on thermal ADS2. So we're also going to do this at finite temperature in ADS2. But then basically, we're going to see what are the roles of these interactions. So the fact that you have these couplings, how do they affect the 2-point function? And basically this coefficient here that I'm highlighting in orange, it's basically controlled by what are the terms that appear here. And also this constant A that I'm writing down there is basically the fact that, so in the context of near ADS2, this field Y is a background field because it defines for you what it meant to go out of the throat. So basically, as you look at the correction of the 2-point function, you're treating this field Y as a background field, and this A is basically the source. Okay, so it's how much did you turn on the background field? Okay, very good. Are we all good still? Yeah, I saw a thumbs up. Okay, great, good. So let's enter this suit. So that's the setup, okay? So we're going to look at the spectrums and we're going to look at this interactions. So let's build our periodic table. Let's pretend that we're chemists. Okay, so there's going to be 2 axes that are going to be interesting to explore that I already mentioned, the case that you have black holes in the ungauge theory and the case that you have gauge black holes. And 2 things that are going to be super important. Of course, black holes come with all sorts of charges and stuff, but the 2 things that I want you to remember for today, the 2 main features about the background, if it's BPS or non-BPS. So this for you, think of this as the surrounding and this basically as properties of the background, okay? Now, as in a good zoo, there's animals, and so I'll be depicting basically in each of these categories, there will be a different animal, and I leave it up to you to interpretation. Why did I select it for each of those cases a specific animal? So you'll tell me at the end of the talk if you're curious why those animals are picked for a reason. Okay, good. Okay, so let's start with the first simplest example, which is the Ungauge theory and BPS black hole. So let's start with the elephant. So basically what we're doing, so in this whole machinery, we're deforming away from ADS2. Basically, I'm grabbing a supersymmetric black hole in an STU model. So these are favorite black holes that you learn from your string theory class, and the black holes that we have the most precise statements about what their extremal entropy is. And in this context, we're trying to see what happens to this entropy, or what happens to this description. Basically, how can we interpret it in the context of near ADS2? And this is also the case where trying to understand the spectrum is pretty straightforward. And what happens is basically there's no mixture between these things. So this is one of like the boring cases. And it's quite cute that all of these fields, so all of these orthogonal states that you build, they all have conformal dimension equal to 2. Very nice. It's basically reflecting the fact that from the point of view of Minkowski 4, all of these fields are massless. So that's why in ADS2 they have conformal dimension 2. Now, this is very related to what Finn Larsen back in 2018 called the N-attractor mechanism, basically saying, so recall that our favorite Y field that appears in JT gravity also has conformal dimension 2, and it's kind of nice and interesting to see that if these fields so this moduli that starts at an attractor point here, so it starts at a constant value, the way that it responds, so the growth in R, so because they both are conformal dimension 2, they both grow in the same way, okay? So that's a fact, and it was first described in this context back in 2018. Now, in terms of the interactions, also the number that you get is very nice and simple, very elegant. This d tilde, you compute it very carefully, and it's 3 over the ADS radius, the ADS2 radius, okay? So that's a simple case. Very good. Now, let's do a more non-simple case. So let's go into the Ungauge theory and just look at non-BPS black holes. It's actually, there's very simple ways how you can construct, so starting from an extremal solution, if you know what the supersymmetric ones are, there's very simple ways how you can construct the non-supersymmetric ones. You basically flip, like one simple way how to do is flipping a sign and a charge. So this is what people sometimes call almost BPS solutions, but okay, they don't preserve any supersymmetry. And this is what happens in this case. So here I'm listing in the table. So you can see there's already a difference with respect to the supersymmetric case. So the first thing is that, okay, so there's 3 states, basically 3 combinations of these guys that will correspond to conformal dimensions, operators with conformal dimension 2. Great. There's one guy that is even more irrelevant. There's an operator with conformal dimension 3. But there's 2 states that have conformal dimension 1. Okay. This corresponds to basically a marginal deformation. And in the literature, so if you go back to the day when the attractor mechanism was fashionable and the hot topic, this is basically what was trendy to do when I was a grad student, but that reflects how old I am. So, so back in the day, people talked a lot about the attractor mechanism, and this statement translated into that context means that you basically have flat directions in the attractor. Okay, so that in the context for from the point of view of these fields, it means that there are 2 linear combinations of those fields that don't get fixed at the horizon. Their constant values can be whatever they want to be, and it's the same thing, okay? And so that's, in the analysis here, it gets represented by having an operator of conformal dimension 1. Now, so that's already interesting. It ties the old and the new from this point of view. But what is problematic in this example is that because you have this spectrum of operators, so this has been giving me, Evita can tell you all about the headaches that we've had with this very naive and simple example, is that if you start doing your actual effective field theory expansion and start looking at what happens to the interactions, this case, so what we're reporting in D, let me just write it down here very briefly. So we had basically interactions that were of this form, so 2 zetas and 1 y. And what's happening in this context is that if you look at we have to compute a 3-point function here. And for these values, you basically have that the conformal dimensions match. They become extremal, okay? This is not super bizarre. Like this happens. So it happens in supergravity. It happens in higher dimensional compactifications in ADS5 and ADS4. They're extremal correlators. It's all fine and good. The thing that is very interesting in those supergravity contexts, and I'm already running a little bit short on time, so I was good that I didn't delve too much in the details, but there's something very, very problematic in this case, is that usually when we encounter inconsistent truncations, when we encounter extremal correlators, their cubic couplings vanish. And I did not write down here for you the Lagrangian because, I don't know, I just didn't. But in this case, as you do the near ADS2 holographic analysis, these cubic couplings do not vanish. And that means if you ever computed a 3-point function in ADS CFT, it means that the number here, so here I was pretty nice, but basically it means that what we get down here is a big fat infinity. The effective theory is ill-defined. It gives you a divergence. And I get upset. I hope you're also upset. I am very upset. Okay, so that's what happened for non-BPS black holes. There's other extremal couplings. So let me also remark here. So there's other extremal correlators because you have 1, 2 plus 3. So you can have basically, you can note that delta 1 plus delta 2 is equal to delta 3, or also that delta 2 is equal to delta 1 plus delta 1. And all of these have vanishing. So one thing that we did show, so actually, if you look at the extremal occurrences that occur among them, they do have vanishing couplings. So there is something that works here, but basically when you make them talk with the JT field, the extremal coupling did not vanish. Okay, that's a puzzle. And I don't have anything else to say about that, but I am upset, that's all. Okay, now moving to the gauge case. So in the gauge case, there's further technical difficulties. Gauge black holes, but black holes in ADS, they're just more complicated, period. Like there's not, like anyone that has tried to build solutions or characterize solutions in ADS will appreciate that they tend to be slightly more complicated than their ungauge counterparts. And in the context of the discussion that I'm presenting today, one of the complications is that things mix. So the cosmological constant in ADS4 basically introduces inhomogeneous terms between the fields, the moduli and this field Y. And also the metric here enters, you have to treat it carefully. So the metric is also coupling to these fields in a non-trivial way. So as you build the spectrum of operators, you kind of have to disentangle all of these things. Now, one comment in regard to, because these black holes do have a version of the attractor mechanism at the horizon, want this linear dependence on Y is a little bit of a leftover from this N attractor, okay? Because this is basically telling you, and you can see it in the solutions in gauge supergravity, that if you look at how the fields on a solution react as they move away from extremality, they would also have basically, they will look naively as if they're operators of conformal dimension 2, but it's just that there's a non-trivial mixing. In the ungauged case, you do not have this, this mixing between the fields. Okay, very good. So our degrees of freedom from the point of view of what the moduli is doing is basically contained in here, okay? This is already accounted for by what we will call the JT sector. Very good. So let's look at the gauged BPS case. So these solutions date back to these two gentlemen that were the first ones that basically found a BPS solution. It took quite a while. It was highly non-trivial. And for the solutions that we're studying now, so we'll be focusing only on magnetic cases, a holographic description of the entropy in the context of ADS4 CFT3 was given by these authors. And so as we look at the spectrum of operators for BPS black holes in the gauge theory, this is what happens. Okay, so just so you can see already, there's quite a lot of differences relative to the ungauged case. Okay, so I have all sorts of flavors and types of things that can happen. So the first one, so we have, let's start from the bottom. So we have one state that is more irrelevant than the JT deformation, which is okay, it's good. That also happened in other examples. Then you have, for this magnetic cases, you have some operators that lie between 3/2 and 2. Then you also have operators, you have one operator in this case that lies between 1 and 3/2. And then you have basically these operators that lie, their masses are negative, but they're basically between the BF bound. They're still above the BF bound, but below 0. So that's why I'm writing here that there's a plus minus, because you have to consider the two signs for the conformal dimensions. Now, what's interesting in this case, something perhaps I naively was not expecting just by looking at the spectrum of operators. Maybe it's natural for some members of the audience, but I was not expecting it, is that if you look back at the literature, in particular, this paper by Maldacena, Stanford, and Young, they are very careful to argue that the Schwarzschild mode is actually the dominant effect if the matter sector has conformal dimension bigger than 3/2. And that's not happening in this case. I can't see your faces. I don't know if I see, like, maybe, I don't know. Okay, it was shocking to me, because this means that we do have to revisit what is the role of the Schwarzschild theory for BPS black holes in gauge supergravity. Okay, you do have operators that basically will violate, or naively, they're violating the hypothesis that we started with. Okay. So that's what happens in gauge BPS black holes. Now, non-BPS black holes in the gauge theory, they're a little bit more boring, but I don't know, it brings back memories. It's like opening a closet that is a little bit dusty. They exist, they've been there for a while, but because they're not supersymmetric, maybe, well, I don't know, maybe I forgot about them, but now I remember them. They're there, they're pretty. The thing though that happens to them is that, yeah, so you also have an operator that is more irrelevant. You also have some things that lie between 3/2 and 2. But what happens here as well is that you also have two states that actually, as well, not too surprisingly, they violate the BF bound. So these actually become unstable. So it's a difference between the BPS and the non-BPS case in the gauge theory, is that you have violations for the BF bound. If you are someone that works in ADS CMT, you would not be too surprised about this statement. It rings a bell. So in solutions that are of the form ADS2 times R2, this is very, very common. We're just making a remark that if you have ADS2 times S2, it's also happening there. But yeah, this is an old story, and it ties very beautifully with the literature in that other context. Okay, so so from this point of view, these guys are pretty problematic. But okay, that's what happens to the BF bound. Now, for these guys, I didn't state the interactions because it's quite complicated. And then Evita did the most amazing table ever in the world. So to summarize everything that happened, so I copied the table from our paper so that you can see basically what's happening all in one swoop. And I'm going to be doing good in time. So let me just summarize. So the big summary of everything that I have said to you. So I've been talking about the spectrum and the possible interactions. And here, for instance, so this table is split in two. So here the top is the ungauge case. And here at the bottom is the gauge case. And here they're listed basically what are the values of this interactions. We wrote the ranges because the formulas are not very pretty. They're quite nasty. So they're computable. Like you can compute what this d tilde is as a function of the charges and the cosmological constant. But okay, we thought that it was more instructive to just basically, for the purposes of the table, to report on what are the ranges. And what I want to highlight here is that in many of these cases, these interactions are positive, okay, but you can see here that sometimes the ranges of the interactions can flip signs, so they don't always have, the cubic couplings don't always have a definite sign. This is important for the context of trying to build an SYK-like model. So I should remark right now that you can also capture this type of corrections in SYK, but the sign of the interaction that does not depend on which type of operator you have, as far as I've seen. So maybe those models are too simple, but they will not be able to accommodate for all of the stuff that you have down here. So, okay, so that's my summary. So nice, so many numbers. So this is basically the first version of our periodic table. Oh, and I should also remark here, so here we're writing down explicitly as well, what are the eigenstates, so how these zeta eigenstates are related to the moduli that you usually use in the theory. Okay, very good. So let's start wrapping up. So outlook. So what are some lessons that I like to do? Okay, that's one lesson. So the thing that I want to highlight here in terms of like the analysis is that there's quite a lot of differences depending if your favorite Bryson-Ostrom solution is embedded in a way that it makes it supersymmetric versus non-supersymmetric. I'll comment that in the next slide, that this has also already been noted in another type of work. It's also clearly, there was a lot of very important differences in terms of just looking at what would be basically the operators that this dual description will have. Of course, they're very sensitive if you're in a gauge or ungauge case. There's all flavors of operators. So you don't have to, like the supergravity theories that I'm looking at, they're not exotic. Like I'm not picking something very strange or particular. Like these are like the plain vanilla versions of supergravity. And even in those cases, you can see that you have all sorts of different types of deformations. The moduli are doing different things depending on basically on which axis here you are. Okay, there were some expected pathologies. By that I mean the violations of the BF bound that we found here. It's not too surprising, but then there was some unexpected pathologies that were related to the non-vanishing of cubic couplings in the ungauge case. And the last thing that I want to emphasize is that one thing that it will be interesting to understand is basically how to reproduce these corrections from the point of view of the dual description. And as far as we have investigated in SYK models, it's not possible to encapsulate all of this richness. So we need to be better at understanding what a near CFT1 is and how all of this data that we're basically encountering can be encoded in a dual description. And so with that, if you wanted to know how I'm thinking about the future and what would I do in order to address these aspects, I'll basically tell you, okay, the most obvious thing, these near ADS2 geometries, of course, they have a UV completion, and I think it will be very interesting to understand how and when can we reproduce some of these results from the point of view of the UV and the CFT3 that is dual to it. So the ABGM should know about these features, and it should be captured in there. And for the asymptotically flat cases, we have brain constructions. They're basically forms of the D1, D5 system or the D0, D6 brain constructions. So hopefully there's something to be accounted for about this near ADS2 properties. Now, here also, a lot of the things that I'm doing, they're not going to affect the area law. So that's why I didn't focus too much on the area law besides writing it at the beginning. The spectrum of operators, this matter is basically going to affect your path integral as you're doing quantum corrections, okay? And this can affect basically how we understand, just like how do you understand basically the statistics, the statistical physics properties of this. And it was already noticed in these two papers over here, that even if you think, even in cases where you might think that the Schwarzschild is the dominant effect, there was still very important differences between BPS and non-BPS black holes. But here we're even saying there's even more differences between BPS and non-BPS black holes. And even for BPS black holes, we do have to be careful about how this matter is basically going to overcome some of these effects. And I also should mention that in this context of computing logarithmic corrections at finite temperature, we also had observed in the past that there were important differences in terms of the quantum correction. So what would be actually like the more refined version of understanding the entropy. And I think this deserves a lot of attention and doing it appropriately in the context of near ADS2. Now there's more animals in the zoo. Of course, you can include rotation. You can, in the case of gauge supergravity, you don't have to just consider S2. You can have other Riemann surfaces, or just R2 again, but that has been studied quite a lot. But okay, there's differences in the topology. You can have additional charges. So I did focus for the gauge case a lot on the magnetic cases. And of course, there's extensions to higher dimensions, not just 4-dimensional black holes. And the last thing that I want to mention, this is a little bit of a technical topic, but it's quite interesting that black holes in ADS, they're not, if you look at non-extremal black holes in ADS, they're not always consistent. So they're not always integrable. And I think this is an interesting feature to consider in the context of this whole program of like starting with an extremal black hole and moving them away from extremality. These non-trivial conditions should illustrate to basically have an imprint when you look at them from the point of view of near ADS2. So these are conditions, these integrability conditions, if you want, they're coming from the UV. So how does the IR know about those non-trivial conditions? They're conditions on the mass and the mass and charges of the black hole. So with that, I think I'm done. Yeah.
Okay, thank you.
I'm done.
Okay, so we are running a little bit late, but we still have some time for questions. Yes.
Hey, Ali. So quick question. In this theories where you have these operators that violate the 3/2 bounds that you were worried about because it dominates over the JT sector, do you know what a 4.0 talk would look like in a theory like that? Do you have any reasons to believe that maybe in that case it's not maximally chaotic, or you just really don't know?
The only thing I know is what's in the reference, and they looked at how it affects. I don't think they reported on the 4-point function. I don't know. One has to do it. It's just that because nobody has before seen an example where this is the case. I think nobody bothered to compute it. So it's to do.
Yeah, Sounds
But
interesting.
in the original paper, in the Maldacena for Young paper, what they reported on, maybe someone can correct me, but this is what my memory tells me, is that they looked at what happened to the free energy. So they basically did the one loop contribution of these fields, and the power of M beta is basically the temperature dependence on the free energy is affected.
I see. Thanks.
Okay, some more questions? Well, then I have a quick question. So are you suggesting that in order to capture the non-universal piece, SYK model should be extended somehow by including something extra?
It has to be modified quite dramatically. SYK does not fit it.
I see.
We already know that SYK is not really the right thing because it has all these higher spin states. So it's good for describing the Schwarzschild part, but then we know that it's not quite the dual of any of these things, just because it has too many higher spin states. Well, it has an infinite tower of them. But yeah, but if you wanted some inspiration, like the first thing that you have to account for is that your SYK model should have interactions, of course, and that these interactions should be sensitive to the matter that you have in there and should account for different signs of these corrections. And that's, I have not seen models that I could try to fit into this.
I see, great, thank you. So I think we are running out of time, so let's thank Alejandra again. And also, since this is the end of the conference, I'd like to say a little bit because we have been enjoying this conference here in Ascona, and like any other things, some effort should be invested in order to have this event, especially in the COVID times. And I myself have been helped a lot by the organizers, and we have an excellent team of organizers coming from East and West in Masia's language yesterday. So I think we should thank this time to thank Julian and Suzanne. Suzanne is not around, and also Joao and also Niklas for doing their excellent work. Okay, great. So any announcement from organizers? Or?
No, only that today we might risk being 15 seconds late for lunch because we don't have to come back. So we can be relaxed. No, thanks everybody again for coming. It was great, and I hope to see you again soon or in 3 or 4 years in Ascona whenever the next edition is.
Yes, thanks everyone for coming.